Hello everyone, my name is Jerry and today I'll try to convince you to start using type hints in Python. If you're already using them, that's great, but hopefully you will still learn something new from this presentation. Before we get started, a couple of words about myself. So I'm currently working as a staff engineer / Python competence lead at Wolt. If you haven't heard about Wolt, we are a Finnish technology company mainly known for our delivery platform for food and merchandise. We currently operate in 23 countries. And surprise, surprise, Python is the central part of our technology stack. It's actually not only the data language, but it's also the main web backend language for us. For example, most of the consumer-facing high-traffic APIs are powered by Python. And to make the endpoints in those APIs robust, we extensively use type hints and static type checking. Before we dive deep into the types, let's start with some motivation. Here you can see some exceptions from Wolt's production environment. These are actually screenshots from a Slack channel, a message is sent by a Sentry bot about runtime exceptions that have occurred in the production environment. The unifying factor with all these three examples is that something has unexpected type. Maybe even a more common one is when something is none when it should be something completely different. I bet you have seen these kind of type errors or attribute errors in your Python applications at some point. For example, if we consider the uppermost example, let's play with the Python interpreter a bit. So if I open the Python interpreter and then let's consider that we would have some variable which would be none. Then we would try to do something like this, you would get similar exception. Or the second one, if we would try to use my variable as an iterable, so for foo in my variable we would do something. This would lead to similar exception as it with the second one. All these examples are basically software bugs. We're human, we make mistakes, and that's completely fine. But it's a bummer if we only detect this in the production environment because they have probably impacted the end user already at that point. You might be thinking that maybe we're lacking some testing or don't we have a staging environment or something. Yeah, that's a valid concern, but how about if we could detect this already before running the code at all? Wouldn't that be awesome? Guess what? I have a simple solution for you. Just start using type hints and you will be able to catch this kind of type errors or attribute errors or whatnot offline, maybe already during the development on your own local machine or latest at the continuous integration phase. But most importantly, before it gets deployed to production environment. But how can we catch those errors without running the code? A static type checker is the tool for that. In this presentation, I'll focus on Mypy because that's the weapon of choice for me and us at Wolt. There are competitors from some companies that you may have heard of, and it of course depends on the use case at hand, which one is the best fit. However, if you default to Mypy, I would say that that's the safe bet. I would personally consider Mypy being the de facto at the moment in the community. So when we combine type hints with static type checker, we are able to detect these kinds of issues offline already on our own computer. So if you consider this example, here we have a simple dummy function which has type hints in place. And then there's some other code that's calling that function. And then we run Mypy, aka the static type checker, over that module. It reveals us, for example, on line 9, argument view to my function has incompatible type string expected int. So expecting int, and this is clearly a string. If this would happen during the runtime, that would mean runtime exception and our program would probably crash. Now we can fix the bugs already at our own machine before the code is even deployed anywhere. Alright, so let's just add type hints and use static type checker. Is that enough? Unfortunately not. So thanks to the awesome Python community, we have plenty of awesome packages available, and then we don't need to reinvent the wheel every time because we can reuse code written by others. So how to handle the type safety with your dependencies? First of all, most likely, at least for some of your dependencies, there are already type hints in place in those projects. It has been a clear trend during the past years, especially with popular packages which are under active development, that type hints will be there sooner or later. Just a couple of examples, Flask and PyTest added those a while back. But unfortunately, that's not always the case. So for some projects, actually there are separate projects which contain type stubs for those projects. So basically typing information bundled in a separate project. So for example, if we have a look at the type shed, that's the official place for type annotations for Python standard library and Python build-ins, as well as third-party packages as contributed by people external to those projects. So different people maintaining the type information for the actual projects. For example, if we have a look at the stubs directory here, you can see that there are plenty of projects. Maybe you even recognize some of those. For example, requests is here, and plenty of others. And if you cannot find stubs from here, from the official location, you can of course look from the PyPI. For example, here, if I look for types, I get more than 10,000 results. These package names are usually type something or something types, and well, type stubs for this package. Then Mypy is also often very helpful. So for example, if let's say I would be importing something from requests, and I would run Mypy for that module which is doing that, it would kindly note that I should install the types requests myself. Then if you're out of luck and there are no stubs available for your dependency, you can of course create those yourself. There's actually a nice utility called stubgen which comes with Mypy that can be helpful for generating stubs for your untyped dependencies. You might be thinking that isn't it an overwhelming task to add types for a big dependency, but actually that's not the case because you only need the types for the functionality that you are using from that library. And even if you're willing to add types for the full library, you would need to do it only for the public interface, which is often just a fraction of the code of the whole library. And if you see the effort, please consider open sourcing your stubs so that you can help others. I'm sure there are plenty of people who are in the same situation. Let's quickly have a look at how these stubs look like. So if you consider here on the upper left, this could be the source code of some dependency that you might have. There are no type hints here. Then you would run it through the stubgen. It would generate something like this. Now there are type hints, but those are basically dummy ones. But most importantly, you would not need to see the effort for generating the boilerplate. You could just focus on adding the proper types when you already have the boilerplate in place. And like I mentioned, you would only need to add the types for the functionality that you're using. At this point, you might be thinking that, all right, I have a project I've been working on with that for several years. Is it too late to start using types? Well, the short answer is no, it's not too late. And actually, Mypy supports gradual typing, so you won't need to do one gigantic pull request in which you would add the types for every single signature that you have in your code base. So that's great. We actually did this exercise at Wolt a couple of years ago. Maybe better to say we started this exercise. So back then the biggest Python project was more than 100,000 lines of code, and we started gradually adding types to that. The main learning from this exercise was definitely that you should have strict configuration by default and loose when needed if you are planning to add types for an existing, maybe legacy project. I actually wrote a quite detailed blog post about the topic, so if you're interested, have a look at that. In practice, strict by default, loose when needed means something like this. So here you have the default configuration, which is strict, and here you have looser one for this individual module. So this strict by default basically guarantees that all the new code needs to conform this, which is of course great because you kind of gently enforce the new practice for all the new code. That will help with the adoption, while still kind of leaving the old code as it is. So there's no need to change everything from the get-go. If you're not familiar with Mypy and these configuration flags, just quickly, this disallow untyped defs equals true basically means that you need to have type definitions for all the signatures. While this is flipping it to false basically means that for this module there's no need to have type hints, which is kind of what you want to have for this legacy module. Then if you have a boring Friday afternoon, for example, going on, you can try to get rid of these one by one and make your coworkers happy. Right, if you're thinking that, alright, my project is very mature and has 100% test coverage, should I still bother? Well, if it's a package that others depend on, then I would say definitely yes. That will help the users of your package to start using types, and that will make your package more attractive maybe. If there would be two alternatives available which offer the same feature set, I would definitely pick the one which offers the type hints. Additionally, I wanted to highlight a recent blog post from the urlib tree folks. It's basically a case study what happened when they added type hints into their code base. And if you're saying that your project is mature and well tested, guess what? urlib3 is the second most downloaded PyPI package, so they are certainly mature and they already had 100% test coverage before this adding type hints exercise. The main takeaway from this article is that they discovered a number of bugs just by adding the type hints and static type checking. And if you have that 100% test coverage, that means that you have some code which runs every single line of your logic. There's a tool called monkeytype from Instagram which can be used for automatically filling this type hints or generating the stubs. So if you have that 100% test coverage, you could get a head start for an existing project for adding the type hints. It won't be perfect, but it's a good initial guess, so it could be something to start up with. Alright, so far we have gone through how to type your own code, your dependencies, but unfortunately that's not enough. So quite often static type checking is actually not enough. You need some runtime type checking as well. So let's consider this simple illustration. This could be, for example, some sort of web application. So here's your own code. You have some endpoints maybe to which requests are coming in, maybe with some JSON payloads. Then your app is requesting data from some other API. And of course, as a return, as a response, it gets some data back, or it could be fetching data from database. So here inside your app, you're of course safe with your own type hints and static type checking. But how about, let's say you get a blob of JSON data here. You cannot trust the types of that. You may have all sorts of like expectations of the shape of the data, but you cannot trust them. You need to explicitly check the types on the edge. After that, you're safe within your internals. Luckily, there are great tools nowadays which can help with runtime type checking. For example, Pydantic is one of those. It has gained popularity quite quickly, maybe because of its powering fast API. If you're not yet familiar with Pydantic, here are some simple examples. So consider that we have this my data structure which inherits base model from Pydantic. It has two fields, foo, which should be integer, and bar, which should be boolean. If we create instances of that class, these will be runtime type checked. So for example, for these two lower examples, these will raise Pydantic validation error. For example, here foo is a string while it should be an integer, and here bar is a string while it should be boolean. So this is one case in which it won't raise anything because of course foo is integer and bar is Boolean. But note that in the middle case, it's highlighting that Pydantic tries to be clever by default. So here, this is clearly a float, and this is integer. But if I create an instance with these arguments, it will actually cast foo to integer. So this will become 1, and bar will be false because 0 is a falsy value. Just note that this is the default behavior of Pydantic. You can turn some knobs to make it more strict about this type validations, but most often the being clever is actually helpful for the users. In addition to the base model that you just saw, there's a data class, which is basically a drop-in replacement for the data class that's coming from the standard library. So if we consider this simple example, so we have some function that fetches some data from some API, and then it expects the response data to have this sort of shape. If you use a data class from the standard library for this, you have no guarantees about these types. So if in the payload that you get here in the response, if foo is, for example, integer, it will be this line will execute happily, no exceptions raised. While with the data classes from Pydantic, this thing here, so creating an instance of my API response, these types are explicitly checked. If there's something that you should probably take home from this presentation, take this illustration. I think this combines everything that we have discussed so far. So basically, inside your own code, use type hints, use static type checking. And on the edges of your application, use runtime type checking. By combining these, you will end up with type-safe Python applications. And I guarantee you will sleep your nights better. Note that runtime type checking has always some sort of performance penalty. And because of that, ideally you should be doing the runtime type checking only on the edges. It's basically like running handbrake on if you're using it inside your business logic, for example. So let's, for example, Mypy handle the static type checking in your own code and use runtime type checking only on the edges. Still not convinced? Here's some additional motivation. So if you start using type hints, your IDE or editor or whatever you're using will get superpowers. It will be a lot easier to browse the code, which is important especially if you have a large code base at hand. Then there will be less documentation needs. For example, if you have been documenting the types of the arguments as comments inside the docstrings, there won't be a need for that anymore. And those are usually out of date anyway. These two aspects are especially valuable considering newcomers who don't yet know the code base like the back of their hand. I also argue that there are less testing needs. For example, if you have assert is instance something, there won't be a need for those anymore, because that's already covered by the type hints and the static type checker. Alright, hopefully you're convinced now. Thanks for listening and happy type safe coding with Python. Bye.